Have you ever felt like you're just drowning in data? You've got so much information, all these factors swirling around, and you just need to figure out what really matters.
Yeah, what's actually driving the outcome you care about?
Exactly. Such a common problem, right? Whether you're looking at business results or policy impacts or even like big economic questions.
For sure.
So today we're doing a deep dive into exactly that challenge. We're exploring applied causal inference powered by machine learning and AI.
Mm-hmm.
We're going to look at these really powerful methods that let us answer critical predictive effect questions. The kinds of questions where the old statistical tools just, well, they struggle.
Especially when you've got tons of data, tons of variables, high dimensions as we call it.
Right. So our mission today is really to unpack one specific technique, a really effective one called Double Lasso.
Yeah, we want to get into why it works so well, particularly in these high-dimensional models where you might have way more factors than you have observations almost.
And we're not just going to talk theory, right? We'll look at real-world examples, economic growth, the wage gap, things like that.
Absolutely. And we'll uncover this core principle behind it all, something called Neyman orthogonality. It sounds technical, but it's kind of the secret sauce.
Secret sauce. I like that. Okay, so the goal is you walk away understanding how these cutting-edge tools give you insights you can actually trust.
Yeah.
Robust, reliable insights.
Exactly.
Okay, so let's start with the core question we're often trying to answer. You framed it as, how does a predicted value of y change if a regressor d increases by 1 unit while other regressors w stay the same?
Right. So y is your outcome, could be anything, economic growth like you said, or maybe someone's wage.
And d is the specific thing we're zooming in on. The target, like maybe a country's initial wealth, or for a person, maybe a female indicator variable.
And then W is just everything else you want to control for.
All the other stuff. Education, experience, quality of institutions, market conditions. Could be a huge list.
Exactly. Now, in standard linear regression, finding that effect of D while holding W constant, that's textbook stuff.
Yeah, usually straightforward. But the problem comes when W isn't just a few things, right? What if W are a lot of variables?
That's the high-dimensional challenge. When P, the number of your controls in W, gets large compared to N, your sample size. Well, standard methods just break down.
They become unreliable, noisy.
Totally. Your estimates jump around, your confidence intervals get huge. You just can't trust the results anymore. Can't handle that complexity.
Okay, so that's the problem. Too many controls, traditional methods fail. So what's the solution? What's this analytical power tool you mentioned?
Right. That power tool is Double Lasso. The core idea is something called partialing out. It sounds fancy, but it's basically about isolating what you care about.
Isolating?
How so?
Imagine you want the pure effect of D on Y without all the confusion from W. You first clean both Y and D. You remove the linear influence of all those W controls from both of them. Okay, so you're stripping away the part that's predictable just from the controls.
Precisely. What you're left with are the residuals, the parts of Y and D that aren't explained by W. It's like getting down to the core relationship.
And this idea isn't totally new, is it? I think I read something about Frisch and Waugh.
Yeah, good point. Ragnar Frisch and Frederick Waugh talked about this concept of the logic of partialing out way back. They just didn't have the tools like Lasso to do it effectively when W was massive.
Gotcha. So Double Lasso takes that old idea and gives it modern horsepower. How does it actually do the partialing out, especially with all those W's?
Okay, so instead of using standard regression for that cleaning step, Double Lasso uses lasso regression. And it does it twice, hence the double.
Twice. Okay, walk me through it. Step 1.
Step 1, you run a lasso regression of your outcome Y on all the controls W. Then you run a separate lasso regression of your target variable D on those same controls W.
2 separate lassos.
Okay.
And what do those give you?
They give you the residuals we talked about, the cleaned Y and the cleaned D. We often call them Y tilde and D tilde. They represent the parts of Y and D that aren't linearly predicted by W, according to Lasso.
Now, you keep mentioning Lasso. Maybe just a quick refresher. Why is Lasso the right tool here, especially when W is big?
Good question. So Lasso, it stands for least absolute shrinkage. And selection operator is really smart for high dimensions. It doesn't just estimate the effects of W, it actively performs variable selection.
Meaning it picks out the important W's.
Exactly. And it shrinks the estimated effects of the unimportant ones towards zero, sometimes all the way to zero. This helps prevent overfitting and gives you a much more stable prediction, which is crucial when you have potentially hundreds or thousands of W variables.
Okay, that makes sense. It tames the complexity. So after step 1, we have these cleaned residuals y tilde and d tilde, thanks to the 2 lasso runs. What's step 2?
Step 2 is surprisingly simple. You just run a standard ordinary least squares regression, regress the y residuals, y tilde, on the d residuals, d tilde. That's it.
Seriously,
Yeah.
just a simple regression on the residuals.
Yep. And the coefficient you get on d tilde in that final regression, that's your double lasso estimate for alpha, the predictive effect of d on y, after effectively controlling for potentially tons of w's.
Wow. Okay, so the power comes from using lasso to do the cleaning, the partialing out, in a way that handles high dimensions, and then you do a simple regression on those clean parts.
You got it. And that's why it works where standard OLS just fails. It gives you precise estimates, reliable confidence intervals, even when PAN, the ratio of variables to sample size, is pretty large.
It really isolates the signal. Okay, let's make this concrete. You mentioned the economic growth example,
Yeah.
the convergence hypothesis.
Right, the big question, are poorer countries catching up to richer ones? The hypothesis says yes if their growth rate, Y, is negatively related to their starting wealth. D, once you account for other factors, W.
So how is this set up using Double Lasso?
Yeah. Researchers used data based on the Barrel-Lead data set. They looked at 90 countries, so N90, and they had about 60 control variables, things like education, institutions, trade, stability. So P is around 60.
Okay, P60, N on 90. So PN isn't small at all. That's a tough spot for traditional methods.
Exactly. Y was the annual GDP growth rate. D was the initial GDP per capita, the starting wealth, and W was that big list of control factors.
And what happened when they compared regular OLS to Double Lasso?
The difference was, well, striking. OLS gave an estimate for that convergence effect, alpha, of 0.009. But the confidence interval was huge, negative 0.073, 0.054.
So it includes 0, easily, could be negative, could be positive. OLS basically says I have no idea.
Pretty much. Total uncertainty. But then, Double Lasso, it gave an estimate of negative 0.045, much stronger negative effect, and the 95% confidence interval was negative 0.00 day or 0.010.
Ah, so the entire interval is below 0.
Entirely negative, which is perfectly consistent with the conditional convergence hypothesis. It suggests poorer countries are catching up once you properly account for those other factors using Double Lasso.
That's a fantastic example. OLS is lost in the noise. Double Lasso gives a clear, robust, inferential statement.
It really shows the power. It delivered where OLS just couldn't.
Okay, we've seen it works. But why? What's the underlying magic? You mentioned the secret sauce earlier, Neyman orthogonality.
Yes, Neyman orthogonality. That's the critical property. It sounds a bit intimidating maybe, but the core idea is about robustness.
Robustness to what?
Robustness to small errors in estimating the effects of all those control variables, W. Remember, Lasso in step 1 estimates the relationship between W and Y and between W and D. These are sometimes called nuisance parameters because we don't care about them directly, only about alpha.
Right, we only really care about the D to Y effect.
Exactly. Now, because Lasso uses regularization, the estimates for those nuisance effects might have some slight bias, especially in high dimensions. Neyman orthogonality ensures that these small biases, these little imperfections in estimating the W effects, do not mess up our final estimate of alpha.
Okay, so it prevents errors from like blending over from the control variable estimation into the main result we care about.
Precisely. It makes our target estimate, alpha, what we call first-order insensitive to those nuisance parameter estimation errors.
Can you give an analogy? Like the dartboard one you mentioned.
Yeah, think about aiming at that bullseye that's estimating alpha. Estimating all the W effects is like calibrating your throwing stance, your arm angle, everything else. Neyman orthogonality is like having a system where even if your stance is slightly wobbly or your calibration isn't perfect, small errors in W estimates, your dart still lands incredibly close to the bullseye. Alpha estimate is still accurate.
That helps. The main shot isn't thrown off by minor issues in the setup. Okay, so that's why Double Lasso is reliable. What happens if you don't have this orthogonality? You mentioned a naive method.
Ah, yes, the pitfall. The naive method, or sometimes single selection, seems intuitive, but it's flawed for inference.
How does it work? Or rather not work?
What people might try is Just run one big lasso regression of y on both d and all the w's together. Then they look at which w's lasso kept, didn't shrink to 0, and they run a standard OLS regression of y on d and only that selected subset of w's.
That sounds plausible.
Yeah.
You use lasso to pick the important controls, then run OLS. Why is that naive or flawed?
It's flawed because the underlying moment condition, the equation that implicitly defines the estimate, is not Neyman orthogonal. This means the bias introduced by that lasso selection step can directly contaminate your estimate of alpha.
So the bias doesn't get canceled out or isolated like in Double Lasso.
Exactly. And the specific problem is how it selects w's. It only selects w's based on how well they predict y.
Okay, and why is that bad?
Because you might have a control variable, a w, that isn't a great predictor of y itself, so lasso might drop it. But what if that w is a strong predictor of d, our target variable?
If you drop it, you're creating omitted variable bias for D's effect, even if that variable didn't seem important for Y initially.
You nailed it. That's the core issue. Double Lasso avoids this because it runs two prediction problems, one for Y and one for D. It effectively selects controls that are important for either Y or D, making sure the final residuals are properly D-confounded.
And simulations back this up strongly.
Oh, absolutely. There are simulation studies, like one mentioned in the materials, where they compare these methods. The naive estimator, heavily biased, just as theory predicts. The double lasso estimator, approximately unbiased, well-behaved, Gaussian-like. The difference is stark.
Okay, so Neyman orthogonality is crucial, and Double Lasso achieves it, while simpler approaches fail. Now, what if we care about more than one D? Maybe multiple policies, or how an effect changes across groups?
Good question. Yeah, often we are interested in multiple effects, maybe the impact of several different treatments or heterogeneous effects. Does a policy affect young people differently than older people, for instance? Or maybe even nonlinear effects.
Can Double Lasso handle that complexity?
Yes, it extends quite naturally. You can essentially apply the double lasso procedure, that partialing out logic, one by one for each coefficient you're interested in.
Okay, so you can estimate multiple alphas, but that brings up another issue, right?
Yeah.
Interpreting lots of results at once.
Yeah.
You mentioned simultaneous versus marginal confidence intervals.
Crucial distinction. Let's say you estimate 10 different effects, maybe 10 different alphas, and you calculate a standard 95% confidence interval for each one.
Okay, so each interval has a 95% chance of containing the true value for that specific alpha.
Right, that's a marginal confidence interval. But what's the chance that all 10 of those intervals simultaneously contain their respective true values?
Uh-oh. It's going to be less than 95%, isn't it? Like 0.95 times 0.95, 10 times.
It drops off fast, maybe down to like 60%. 0.951 narrow is about 0.599. So if you just look for any interval that doesn't contain 0 and declare significance, your chance of making at least one false discovery, finding an effect that isn't really there, is way higher than the 5% you thought you had.
Okay, so that's where simultaneous confidence intervals come in.
Yes, simultaneous CIs are constructed differently. They are designed to guarantee that the probability of all the intervals covering their true parameters simultaneously is, say, 95%.
So it controls the overall family-wise error rate, makes your conclusions much more robust when you're looking at a whole set of results.
Precisely. It's a more rigorous standard when you're exploring multiple hypotheses.
Let's tie this to the other example, the wage gap analysis. That seemed to involve multiple effects.
It did. Researchers used current population survey data from 2015. They looked at log hourly wage, Y. The main target variable, D, was a female indicator, but they were interested in heterogeneity.
How the gap changes for different groups.
Right, so they created interaction terms. Female indicator times education level, like some high school, college grad, advanced degree. Female indicator times region, Midwest, Southwest. Female indicator times different powers of work experience.
Wow, okay, so that created multiple target parameters to estimate.
Yep, 12 in total. The main female effect, plus 11 interaction terms showing how that effect varied. And they controlled for a lot of other stuff, about 990 engineered control features in W. Definitely high dimensional.
And what did the Double Lasso results show using those rigorous simultaneous intervals?
Okay, so the main effect, the average difference associated with the female indicator, was estimated at -0.07. And the 95% simultaneous confidence interval was -0.11, negligible 0.03.
So clearly negative, doesn't include 0, suggests a persistent average gap, even with all those controls and using the strict simultaneous standard.
Correct. But now look at the interaction terms, the heterogeneity. The point estimates, just the numbers themselves, showed some interesting patterns, like the gap seems smaller for college grads, maybe largest for the least educated, maybe bigger in the Midwest.
But I sense a but coming.
When they looked at the simultaneous confidence intervals for those 11 interaction terms, almost all of them contain 0.
Ah. So while the point estimates suggested differences across groups, the evidence wasn't statistically strong enough to conclude those differences were real once you account for testing multiple hypotheses simultaneously.
Exactly. The simultaneous intervals told a more cautious story. It showed that while the average gap was significant, the evidence for statistically significant heterogeneity across these specific groups in this dataset wasn't really there, according to this rigorous test.
That's a powerful illustration of why simultaneous intervals matter. You might see patterns in point estimates, but you need the right inference to know if they're just noise.
It really highlights the importance of not overinterpreting individual coefficients when you're looking at many of them.
Okay, so Double Lasso is one powerful tool built on Neyman orthogonality. Are there other related methods that achieve similar goals?
Yes, definitely. The field has developed several related techniques. One is called double selection, which you alluded to earlier.
How does that one work?
It's slightly different structurally, but gets you to a similar place. Step 1. Use lasso to find controls, let's call them WY, that predict the outcome Y. Step 2. Use lasso again to find controls WD that predict the target regressor D.
Okay, 2 lasso runs again, finding relevant controls for Y and D separately. Then what?
Step 3. You run a final OLS regression. You regress Y on D, but include all the controls selected in either Step 1 or Step 2. So you use the union of WY and WD as your control set in the final OLS.
Interesting. So it also ensures you control for anything related to either Y or D.
Yeah.
And this also has that orthogonality property.
Yes. It also effectively achieves Neyman orthogonality and provides valid inference, guarding against that omitted variable bias from naive selection. It's often approximately equivalent to the partialing out approach of Double Lasso.
And you also mentioned debiased lasso or desparsified lasso.
Right, that's another flavor. It approaches the problem slightly differently, often framed more algebraically. It involves constructing an estimate that directly corrects for the bias introduced by the initial lasso regularization.
How does it do the correction?
It often involves using something related to the residualized D, like detailed from before, almost like an instrument for D in an instrumental variable framework, or using specific matrix calculations to debias the initial lasso coefficient for D. The math looks different, but the goal and the underlying principle achieving Neyman orthogonality are the same.
So double lasso, double selection, debiased lasso.
Mm-hmm.
They're all part of this family of debiased machine learning.
Exactly. They all leverage machine learning tools like Lasso for prediction and variable selection within a framework designed to deliver unbiased, robust inference on specific target parameters, even in really complex, high-dimensional settings.
Okay, so wrapping this up, we've journeyed through this world of high-dimensional data where traditional methods often fail us.
Mm-hmm.
And we've seen how techniques like Double Lasso, which are built on this really powerful principle of Neyman orthogonality, give us a way forward.
Yeah, they let us zero in on specific predictive effects, like the impact of initial wealth on growth or a demographic factor on wages, and get reliable answers even when there's a ton of other stuff going on.
They provide robustness against bias, especially the kind that creeps in when you try to select controls naively, and they allow for solid statistical inference confidence intervals you can actually trust.
And the so what here is huge, right? This isn't just academic.
No, not at all. Anyone making decisions based on data in economics, policy, business, healthcare, you name it, needs tools like these.
When you need to go beyond just what happened and understand why, and you need confidence in that why, well, understanding these deconfounding, debiased methods is becoming essential.
It really feels like machine learning and AI are moving beyond just prediction. They're giving us new lenses to see causal relationships in complex data.
Absolutely. It's transforming how we can approach causal questions.
So maybe a final thought for our listeners to chew on. As these tools become more accessible, what long-standing questions in your world, questions that seemed maybe too messy or complex before, might be ready for a fresh look using these powerful orthogonal methods? What intractable problem might finally be tractable?